Okay, what we have here is a graph above shows the changing force acting on a 10-kilogram crate as it's propelled across the floor by the means of a giant slingshot. So it starts off with 40 newtons of force, and as the slingshot projects the object, eventually it gets to where it's applying zero force. Then we see there is a negative 20 Newton force acting on the cart for the remaining 10 meters. So the first question, how much work was done on the crate by the slingshot? When I say work is done on the crate, that means the crate is gaining energy. So I'm adding energy to the crate, and the amount I'm adding is 300 joules. And I get that by finding the area under this curve. So what I do is I take this rectangle here, which is 40 by 15, and then I divide that by 2 because I don't have the whole rectangle. I just have half the rectangle. And when I do that, I get 300 joules, and because the force is positive, these are positive joules, meaning I'm adding energy to the crate by means of propelling it by the slingshot. The second question was, how much work is done by the crate on the floor after it leaves the slingshot? So when something is done, when work is done by the crate, it's going to lose energy. So the crate is getting rid of energy now as it transfers energy or does work on the floor, generating heat energy. And in this case, what I'm going to do is I'm going to measure this rectangle right here. So it did 20 newtons across a distance of 10 meters. So it did negative 200 joules worth of work. So I get negative 200 joules. Now the next question we have is, what is the coefficient of friction acting between the floor and the crate? Now in order to find that, I can't look at the first part of it because I don't know. I can just see what the net force is, but I don't know what the actual force of the slingshot was, just how much work it ended up doing. But in the second part of it I can. I can say, well, here the only thing acting on the crate is the friction with the floor. And so therefore I can say, well, I know it's a 10 kilogram crate, so mg for the crate is going to be 100 newtons. I'm going to use the friction force equation and say, well, I know that I had negative 20 newtons of force is the friction force. I'm looking for mu, and I know the normal force acting on the crate must be 100 newtons. You know, when I solve for mu, I get 0.2. The trick here really is just to understand that I have negative 20 newtons worth of force generated by friction. What is the net change in energy for the crate for the total 25 meters shown on the graph? So between here, a distance of 0 and a distance of 25, at first we did 300 joules worth of positive work, then the crate did 200 joules worth of negative work, and that leaves me with a net change of 100 joules. At the end, the crate has 100 joules more than it had at distance 0. Oops, that didn't work. Alright, on to the next one. The graph above shows a 12 kilogram sled being accelerated from rest across a frictionless surface. Oh, thank goodness it's frictionless, by a tension force that's pulling it. So, 5. How much work was done by the tension force on the sled by the time the sled had gone the full 25 meters? So what I have to do is I have to do a series of rectangles and triangles and calculate the area of each. Because remember, the energy or work done is equal to force times distance. So that equals the area. So I have 5 times 10 is 50 divided by 2 gives me 25. Then I have 10 times 10, that's 100. Then I have 10 times 5 is 50. And I have 20 times 5, and cut that in. Is that right? I have 10, 20 times 5 is 100, and then I divide that by 2, I get 50. And then I have 30 times 5 is 150. Now when I add up all of these, add them all up, 25 plus 100 plus 50 plus 50 plus 150, what I get is the total work done is 375 joules. Next question is, how fast is the sled going after it's been propelled for 25 meters? So I know it gained this much energy, and that energy is going to be kinetic energy since the floor is frictionless. So I'm going to use the kinetic energy equation. I'm going to substitute 375 joules, the work done on the sled, for the kinetic energy, equals half the mass, which is 12 kilograms, times v squared. And when I solve for v, I'll get 7.9 meters per second. Don't forget this is squared, so you'll have to basically divide 375 by half of 12, which is 6, and then take the square root. That's how you get 7.9 meters per second. Number 7 asks us, how fast is the sled going when it had been propelled 15 meters? So at which point I have to say, well, at 15 meters, what was the total work done? Well, it was 125 joules. So I'll use 125 joules, substitute that in for K. 125 joules equals 1/2 of 12 v squared. And this time, when I solve for v, I'll get 4.6 meters per second, which makes sense. It should be less than the 7.9 I get at the end of all of it. Welcome to the back side of your homework. Let's see what we've got. The graph above depicts the amount of force acting on a 45 kilogram rocket sled as it's propelled across a frictionless, frictionless surface, but then being slowed down while encountering a high friction surface. Don't ask me why it says period surface. Okay, number 8. What is the total amount of work done on the sled by the rocket? So let's see. What we have here is, at first, we have 30 newtons times 10, that's 300, but we only have half of that, so that's 150. Then we have 30 times 5, that's another 150. Then we have no force, then we have the friction force. So really, the rocket did this, and so the grand total of those two areas right there is 300 joules. Now what is the amount work done by the sled on the high friction surface? So now the force is acting the opposite way. I have 40 newtons of force slowing it down, and the work needed to do that is going to be 40 times 5, which is 200 joules. What do we got next? What is the coefficient of friction acting between the sled and the high friction surface? So in order to do that, I have to first figure out, first I need to figure out mg. So since it's a 45 kilogram rocket, mg is going to be 450. Since this is a flat surface, that will also be the normal force. I'll now use the friction equation and solve it for mu. So the friction force is right here. It's negative 40. I'll just say 40 because we really want the absolute value of it. And then the normal force is 450. So 40 divided by 450 gives me a mu value of 0.09. Then, assuming the rocket started from rest, how fast was it going in the following positions? So after 10 meters. So at 10 meters, we had 150 joules worth of energy added to the rocket. So I'm going to solve the kinetic energy equation for V, and I have the rocket going 2.6 meters per second. After 15 meters, it had the full 300 joules of kinetic energy. So when I solve for V, I get 3.7 meters per second. Now at the 20 meter mark, I haven't done any more work. It's just traveling at a constant speed of 3.7. It went from 0. At this point, it was going 2.6. Now it's going 3.7. Now it's going 3.7. Now it's going 3.7. So the answer is 3.7. Sound like a crazy person doing that. At 25 meters, I have to see what the net amount of work is. So we have 300 joules worth of positive work that was done here. And we have 200 joules worth of negative work that was done here. So when I take 300 and negative 200, what I get is 100 joules. And 100 joules of kinetic energy is going to give you 2.1 meters per second. Alright, now this next one, I've seen examples like this on the release items for the AP, and so they're trying to simulate real world data, and I think I could have done a better job. I tricked myself here, mostly because it was hard to tell where 10 was. So basically, this is where I meant to have it start leveling off. So what we see is we start at 20, we climb till we get to here, then it stays level, and then I get this downward trend here. That's what I was shooting for. So, and also, I hope you added on to here that it was a 6 kilogram toy car. I somehow forgot to add that there when I first printed this. So, 11. At what distance from the start line did the car apply the brakes? Now, when you apply the brakes, you have a negative force acting on you. So, although I started with 20 newtons of force and built to 40 and then maintained 40, and then it gradually drifted off down to 0, it isn't until this point here where I go negative that the brakes are applied. So the brakes got applied at the 20 meter mark. What is the car's maximum velocity? Well, it's gaining energy this entire time until you apply the brakes. So that means I have to divide this up into several triangles and rectangles. So I have a 200 joule rectangle here, and here I have a 100 joule triangle. I have another 200 joule rectangle here and a 100 joule triangle here. So if I add those up, when I add all those up, what I get is 200 plus 100, that's 300, 400, 500. I have 600 joules worth of energy the car gained. And then I'm going to use the kinetic energy equation with those 600 joules. 600 joules equals 1/2 the mass of the toy car, v squared. And so 600 divided by 3, take the square root, that gives me 14.1 meters per second. And what is the car's final velocity when it gets to the 25 meter mark? Well, what happens there is I take this 600 joules that I've acquired up to this point, and we have to take away 50 joules that the brakes have applied. So the change in energy at that point is 550 joules. I put that into my kinetic energy equation, 1/2 of 6 times v squared, and when we do that, what we find is the car has slowed down to 13.5 meters per second.